In this video, we discuss how to construct a fault-tolerant quorum system. We assume that you are familiar with the grid quorum system, as shown here in the picture, with one example quorum marked. Is the grid quorum system fault-tolerant? As you can see, if we crash a bunch of nodes, the orange quorum is not available anymore, since two of the nodes in the orange quorum have crashed. But the quorum system as a whole is still intact. For instance, the green quorum is still available, since all of its nodes are still intact. So a client that accesses the green quorum can still make progress. The fault tolerance of a quorum system can be measured by its resilience. We call a quorum system F-resilient, if at least one quorum is unharmed after crashing F nodes. However, a quorum must still be available no matter which F nodes crash. If you place the 10 crashes more strategically, can you kill all possible quorums in this grid quorum system? Please pause the video and try to crash 10 nodes such that all possible quorums are gone. There are many possible solutions. For instance, we can just move 2 of the crashes such that we have at least one crash in every row and in every column. This way no more quorum is available. Or we can simply move all the 10 crashes to the last row. This also eliminates all quorums. So, the 10 by 10 grid quorum system is not 10 resilient. But is it 9 resilient? Please pause the video and think about this. If you can only crash 9 nodes in a 10 by 10 grid, then no matter which nodes you crash, at least one row and at least one column must be crash-free. And this row and column is exactly where we can find our unharmed quorum. So we showed that a 10 by 10 grid is indeed 9 resilient. And in general, with the same argument, a k by k grid is k-1 resilient. Let's compare our quorum systems regarding resilience. We have just seen that the grid has a reasonably good resilience since roughly a square root of the nodes can crash. The single server has the worst possible resilience. If the single server is out of order, the only quorum is gone. So the single server has 0 resilience. Regarding resilience, the majority system is great, as almost half of all the nodes can crash, and we still are guaranteed to have an available quorum. This was a worst-case view, a common view in computer science. What about an average case view where the nodes crash with some probability? Say, each node fails with some probability q, and survives with probability p, where p is equal to 1 minus q. We consider pi to be a constant value which is higher than half, so the chance that a node survives is strictly higher than the chance that it fails. If you prefer concrete values, think of a node surviving to have probability 2/3. As you can see, such a probabilistic failure scheme seems to be bad news for the grid quorum system, as it becomes very difficult to have any quorum surviving. Assuming that each node failing is independent of all other nodes. What's the probability that you find a valid quorum? Let's do the actual math. This is a good exercise. Assume we have a k by k grid for large K, and we want to know whether any quorum survives. If any quorum should survive, we need a full row to survive, because any quorum needs at least a full row. More things are needed, but the probability of some quorum surviving is surely not higher than the probability of a row surviving. Now this is exactly the opposite of no row surviving, it's equal to 1 minus that probability. In our k by k grid there are k rows, their survival probabilities are independent, so we can just do the computation for one row, and multiply that result k times with itself. Then we do the same trick again, and instead compute 1 minus the probability that this one row is actually surviving. One row surviving means that all k nodes in that row survive, which happens with probability p to the k. So in total, we get 1 minus and then 1 minus p to the k, and this to the power of k. We can use the Bernoulli inequality to simplify that expression as follows. With large K, this expression becomes 0. This is bad news for our grid quorum system, as it is really not good at handling random crashes. Let's go back to our overview table. We just computed the result in the bottom right cell, showing that the probability to survive random node failures goes towards 0 for the grid quorum system. For the single server, we simply need to take the probability of the single server failing, which is q. This is also not good news, because eventually, over a long time, that single server might fail. The simple majority system, on the other hand, does very well in this respect. With the number of nodes being high enough, we can assume that a majority of the nodes survive. If the number of nodes is large enough, in the limit we can even say that the system survives with probability 1. In this table, a green entry generally means good news, a black entry means okay news, and a red entry means bad news. So the main question is whether we can fix the grid quorum system somehow to make that red entry in the bottom right corner green. And indeed, this is possible. There exists an intricate generalization of the grid quorum system which can handle random crashes well. This system is known as the B-grid. It is more complicated than the grid, and it generally pays for everything with higher constants, but asymptotically it manages to get the same functions as the grid quorum system regarding work, load, and resilience. But on top of that, its probability to survive failures is 1 in the limit. So how does this B-grid work? Well, it's basically a grid, but we group horizontal rows together into so-called bands. In this image, each band consists of 2 consecutive rows. The total number of nodes is the product of columns, bands, and then the number of rows in each band. Let's look at an example quorum. Each quorum in the B-grid needs a mini-column in each band, but that mini-column can be in an arbitrary column. If we choose the size of the variable r to be logarithmic in the number of nodes, we can achieve this with high probability. For one arbitrary band, in our example quorum the lowest band, we additionally need to choose one node for each column. Also, this exists with high probability if the band size is logarithmic in the number of nodes. Altogether, such a quorum system can survive even probabilistic failures. And you can check that this quorum overlaps with any other quorum constructed the same way, because the mini-column in the main band of the other quorum will guarantee that there is a node which is part of both quorums. So far, we exclusively talked about crash failures. What about other popular failures, for instance Byzantine failures? To tolerate Byzantine failures, quorums must overlap more substantially. If 2 quorums just need one node in common, then that node might be Byzantine. So in order to make Byzantine quorum systems, we have to make sure that any 2 quorums have a large overlap to tolerate a number of Byzantine nodes. Because of this large overlap, it's often not practical to build grid-like Byzantine quorum systems. With Byzantine failures, we fall back to simply asking all the nodes in the system. Let us summarize this video. We introduced 2 failure models. Resilience is good for worst-case crash failures, and failure probability is good for average-case crash failures. The B-grid is doing well regarding both of these failure models. Thanks for watching this video.